Establishing a Mars communication network by 2025. Overview. As humanity prepares for deeper exploration of Mars, the establishment of a robust communication network between Earth and Mars has become a critical focus. With an investment of approximately $500 million, the initiative aims to ensure seamless connectivity to support upcoming missions, including NASA's Artemis program and various endeavors by the European Space Agency (ESA). This report outlines the core technologies that will be leveraged for the communication network and details the development timeline. Core technologies. To achieve reliable communication between Earth and Mars, three core technologies have been identified. 1. Laser communication. Laser communication represents a leap forward from traditional radio frequency methods. Utilizing lasers for data transmission offers several advantages. Higher data transfer rates. Laser communication can transmit data at much higher speeds compared to conventional radio waves. Increased data bandwidth. This technology allows for more data to be sent simultaneously, which is essential for transmitting high-resolution images and scientific data. Reduced latency. The lower latency achieved through laser communication is crucial for real-time interactions, particularly important for manned missions where astronauts need instant feedback. 2. Satellite networks. A constellation of satellites orbiting Mars will provide continuous coverage, ensuring consistent data transmission back to Earth. Key aspects include global coverage. The satellite network will ensure that all regions of Mars are accessible for communication, which is vital for both manned and unmanned missions. Support for diverse missions. This network will facilitate communication for various missions, including rovers, landers, and potential human habitats on the Martian surface. 3. Autonomous routing systems. Efficient data traffic management will be achieved through autonomous routing systems, which will adapt to dynamic conditions. These systems will automatically adjust communication pathways based on environmental conditions and spacecraft locations, ensuring uninterrupted service. Optimize data flow. By directing communications through the most effective routes, these systems will enhance the overall efficiency of the network. Investment and development timeline. The proposed investment of $500 million will be allocated toward the development and deployment of the necessary infrastructure and technologies. The timeline for establishing this communication network is ambitious, with a target date set for 2025. The development phases include initial technology demonstrations, testing laser communication. Early trials will focus on validating the effectiveness of laser communication in space environments. Satellite prototyping. Prototypes of the satellites will be developed to test their functionality in Martian conditions. Satellite launches. Deployment of constellation. The satellite network will be launched in phases to build a comprehensive communication system around Mars. Setting up ground stations. Ground stations on Earth. Ground stations will be established to receive and process data transmitted from Mars, ensuring that information is relayed promptly to mission control and research facilities. Key points of consensus. Several key points emerge from the analysis of the sources involved in this initiative. Critical nature of communication. Reliable communication is deemed essential for the success of Mars missions, allowing scientists and engineers to monitor and support missions in real time. Integration of advanced technologies. The combination of laser communication, satellite networks, and autonomous routing systems is seen as vital for achieving the ambitious goals of Mars exploration. Need for collaboration. Achieving these objectives will require collaboration across various sectors, including government space agencies, private companies, and academic institutions. Differentiating perspectives. While the core technologies and investment strategies are widely recognized, different sources emphasize varying aspects of the initiative. Technical focus. Some sources delve deeply into the technical specifications and advancements of the communication technologies. Strategic importance. others highlight the geopolitical and strategic implications of establishing a communication network for space exploration, positioning it as a cornerstone for international cooperation in space. Conclusion: the establishment of a Mars communication network by 2025 hinges on leveraging cutting-edge technologies, securing substantial funding, and fostering collaboration among global stakeholders. The focus on high-bandwidth communication is pivotal as humanity prepares for deeper exploration of Mars, making this initiative a cornerstone of future interplanetary endeavors. With the successful implementation of these technologies, seamless communication between Earth and Mars will not only enhance mission efficiency but also lay the groundwork for humanity's long-term presence on the Red Planet. Counterintuitive information in the Mars Communication Network Initiative. 1. Investment versus expected outcomes. The initiative proposes a $500 million investment for establishing a communication network by 2025. While this amount seems substantial, it may be counterintuitive given the complexity and scale of space communication technologies needed. The expectation that such a budget can deliver high-tech solutions like laser communication and autonomous routing systems might underestimate the actual costs involved in space exploration technology development, which often requires billions, not just millions. 2. Laser communication versus traditional radio frequencies. Although laser communication is heralded for its high data transfer rates, there is a significant challenge with atmospheric conditions on Mars and Earth, as well as alignment accuracy over vast distances. This counters the common belief that moving away from radio frequencies will inherently solve communication issues. The practicality of using lasers in a Martian atmosphere, which is thin and dusty, may present unforeseen challenges that are not as prevalent with radio waves. 3. Autonomous routing systems. The reliance on autonomous routing systems may seem like a straightforward solution for managing data traffic. However, this approach could inadvertently introduce risks such as the potential for system failures or misdirection of data packets. The assumption that automation will streamline communication overlooks the complexities of ensuring reliability in an unpredictable environment where latency and error margins are critical. 4. Collaboration dynamics. The initiative emphasizes collaboration among various space agencies, private companies, and academic institutions as essential for success. However, the complexity of such partnerships can lead to bureaucratic delays and conflicting priorities, which might hinder rather than expedite progress. The expectation that collaboration will automatically lead to faster development may be overly optimistic given historical challenges in international space projects. 5. Aggressive timeline. Setting a 2025 deadline for the completion of the communication network is ambitious and arguably unrealistic. The intricacies of space technology development, testing, and deployment typically require longer timeframes. The belief that rapid technological advancement can overcome traditional timelines may not account for the unpredictable nature of space missions and the iterative process of technology testing and validation. 6. Focus on manned missions. The initiative seems to prioritize communication for manned missions, potentially at the expense of robotic missions. This could be counterintuitive considering the increasing importance of robotic exploration in gathering data and preparing for human missions. The assumption that human presence necessitates the most advanced communication solutions might lead to neglecting the foundational needs of unmanned missions, which are equally critical for successful exploration. 7. Data bandwidth versus latency. While higher data bandwidth is a clear advantage, the counterintuitive aspect lies in the fact that reducing latency is often just as important for effective communication. The focus on bandwidth improvements could overshadow necessary developments in latency reduction, which is vital for real-time communication and operational efficiency, especially during critical mission operations. 8. Earth-Mars connectivity needs. The emphasis on seamless Earth-Mars connectivity might overlook the importance of localized communication networks on Mars itself. This implies that while connecting to Earth is essential, the infrastructure required for internal Martian communications between rovers' habitats, etc., is equally vital. The assumption that a direct line to Earth suffices may miss the operational complexities of Martian surface communication. 9. Technological integration. The initiative's reliance on the integration of advanced technologies may not fully consider the compatibility issues that often arise during real-world implementations. The assumption that these technologies can be easily integrated into a coherent system might underestimate the engineering challenges and the potential for significant setbacks during the integration phase. 10. Public-private partnerships. The expectation that private companies will take on a significant role in developing space communication technologies could be overly simplistic. While private investment is crucial, the complexities of space operation and the high-stakes environments often lead to hesitance among private entities to fully commit resources without guaranteed returns, which can stall initiatives that rely on such partnerships. Conclusion. The establishment of a Mars communication network by 2025 is an ambitious and complex initiative that carries several counterintuitive aspects. While the proposed technologies and investment levels appear promising, the realities of space exploration technology integration and the dynamics of collaboration suggest that achieving these goals may be more challenging than anticipated. Understanding these nuances is critical for stakeholders involved in the project to navigate the path forward effectively. The initiative to establish a Mars communication network by 2025 is a significant undertaking that has implications beyond mere technical advancements. While many reports highlight the core technologies and investment necessary for this project, several important aspects may be overlooked by the general audience. Here are key points that deserve more attention and their significance. 1. Interagency collaboration. The establishment of a Mars communication network calls for collaboration between various space agencies, private companies, and academic institutions. This level of collaboration is not just about sharing resources but also about pooling expertise and knowledge. Many reports may emphasize the technological aspects but understate the complexities and challenges involved in aligning the objectives and methodologies of diverse organizations. Significance. Shared goals. Collaborative initiatives can lead to shared goals that enhance the overall mission of space exploration. The pooling of resources can also help in mitigating risks associated with technological failures or budget overruns. Innovation transfer. Different agencies and companies bring unique innovations and methodologies to the table. This can lead to breakthroughs that may not occur in isolated environments. 2. Long-term infrastructure planning. The focus on immediate technological solutions, laser communications, satellite networks, and autonomous routing systems, can overshadow the necessity for long-term infrastructure planning. A sustainable communication network requires ongoing maintenance upgrades and the ability to scale as technology evolves. Significance. Sustainability. Establishing a sustainable infrastructure is crucial for long-term missions to Mars and beyond. The initial investment of $500 million may cover initial setup costs, but ongoing funding and strategies are required to ensure the network remains operational and effective over time. Future missions. The infrastructure established for Mars communication can serve as a foundational framework for future interplanetary communications, making it essential to plan with foresight. 3. Regulatory and compliance issues. While the technological advancements are highlighted, the regulatory and compliance landscape surrounding interplanetary communications is often under-discussed. Space communication must adhere to international treaties and guidelines such as the Outer Space Treaty, which governs the use of outer space. Significance. Legal framework. Understanding and establishing a legal framework for Mars communication is critical to avoid conflicts over bandwidth and frequencies that could arise as multiple nations and companies pursue their own missions. Global collaboration, regulatory compliance can facilitate international cooperation, which is essential for the success of global space exploration efforts. Aligning on standards can lead to better resource sharing in joint missions. 4. Cultural and ethical considerations. As space missions become more frequent, the cultural and ethical implications of human presence on Mars and the potential for contamination of extraterrestrial environments are crucial issues that should not be overlooked. Significance. Preserving Martian environments. There is a moral responsibility to ensure that Mars is not irreversibly altered or contaminated by human activities. Developing communication systems should include protocols to minimize human impact. Public engagement and education, involving the public in discussions around these ethical considerations can foster greater support for space missions. Transparency in addressing these concerns can help build trust and enthusiasm for future explorations. 5. Data management and cybersecurity. The sheer volume of data that will be transmitted between Earth and Mars necessitates robust data management and cybersecurity measures. While technology is discussed, the protocols for protecting sensitive information and ensuring data integrity are often glossed over. Significance. Data security. As missions become more data dependent, ensuring the security of communications becomes paramount. Cybersecurity breaches could jeopardize missions and lead to loss of critical data. Data utilization. Effective data management strategies will not only protect the information but also enhance its usability for scientific research, mission planning, and operational efficiency. 6. Economic implications and ROI. The proposed $500 million investment raises questions about the economic implications and the return on investment ROI for stakeholders involved in the Mars communication network. Significance. Economic viability. Understanding the economic benefits such as potential commercialization of technologies developed for space communications can attract more investment and support for the project. Job creation. The initiative has the potential to create jobs in various sectors including engineering, data analytics, and research, which can have a positive economic impact in both the short and long term. 7. Impact on global space policy. The establishment of a Mars communication network could influence global space policy, particularly regarding space traffic management and the sharing of resources in outer space. Significance. Setting precedents. This initiative can serve as a precedent for future space endeavors, shaping how countries and organizations engage in collaborative efforts and manage shared resources in space. Policy frameworks. Developing effective policies around space communication can help in avoiding conflicts and ensuring that all nations have equitable access to space resources. 8. Human factors and astronaut safety. The technologies being developed for Mars communication are not just about data transfer, they will also play a critical role in ensuring astronaut safety during missions. Significance. Real-time decision-making. High-bandwidth communications can facilitate real-time decision-making, which is essential for astronaut safety and mission success. Ensuring that astronauts can communicate with mission control effectively can be a matter of life and death. Mental health considerations. Long-duration missions can have psychological impacts on astronauts. Reliable communication with Earth can help mitigate feelings of isolation, thus supporting their mental well-being. Conclusion. The initiative to establish a Mars communication network is ambitious and multifaceted, yet many of its critical components may go unnoticed by those focused solely on the technological advancements. By recognizing the importance of collaboration, long-term planning, regulatory considerations, ethical implications, data management, economic impacts, policy influence, and human factors, stakeholders can better prepare for the complexities of interplanetary communication and ensure the success of future Mars missions. The holistic view of this initiative will not only enhance the feasibility of establishing a communication network but also contribute to the broader goals of sustainable and responsible space exploration. 1. Core technologies for Mars communication. The establishment of a Mars communication network relies on three transformative technologies: laser communication satellite networks and autonomous routing systems. Laser communication offers significant advancements in data bandwidth and latency reduction, making real-time communication between Earth and Mars feasible. The satellite network will ensure continuous coverage for both manned and unmanned missions on Mars, while autonomous routing systems will optimize data traffic management. Adapting to the unique challenges of space communication. 2. Investment and collaborative development. A proposed investment of $500 million is crucial for the development and deployment of the necessary infrastructure and technologies to facilitate this communication network. The ambitious timeline targeting a 2025 completion date highlights the urgency and significance of the project. Collaboration among space agencies, private companies, and academic institutions is essential to fast-track the development process, ensuring that milestones are met for technology demonstrations, satellite launches, and ground station setups. 3. Importance of reliable communication. Reliable communication is universally acknowledged as critical for the success of Mars missions. The integration of advanced technologies is deemed indispensable to support upcoming missions, particularly as interest in Mars exploration grows. This consensus underscores the need for a robust communication framework which will enable effective data transmission and communication between Earth and Mars. Essential for scientific research and operational safety during missions. 4. Diverse perspectives on technology prioritization. The discourse around establishing a Mars communication network reveals varying perspectives among stakeholders. Some sources focus on technical aspects and advancements, while others emphasize the strategic significance of these developments within the broader context of international space exploration efforts. Different organizations may prioritize select technologies based on their unique mission goals, such as human spaceflight versus robotic exploration, reflecting the multifaceted nature of space communication development. In summary, the initiative to create a communication network for Mars by 2025 revolves around innovative technologies, substantial investment, the critical need for reliable communication, and diverse stakeholder perspectives on technology prioritization. 1. Apollo program and the development of communication technologies. The Apollo program 1961 to 1972 was a significant milestone in space exploration, particularly for its advancements in communication technologies. The program required robust communication systems to maintain contact between astronauts on the Moon and mission control on Earth. NASA developed a network of ground stations and utilized radio frequency transmission to relay voice and telemetry data. The success of this program laid the groundwork for future space missions and highlighted the importance of reliable communication systems in ensuring mission safety and success. 2. The Global Positioning System (GPS) development. Developed by the United States Department of Defense and launched in the 1970s, GPS revolutionized navigation and communication. Initially intended for military use, GPS became available for civilian use in the 1980s. The system relies on a constellation of satellites that transmits signals to ground receivers, allowing for precise location tracking anywhere on Earth. Its establishment required significant investment in technological innovation, serving as a precursor to more advanced satellite communication networks, including those needed for Mars missions. 3. The International Space Station (ISS) and its communication systems. The ISS, a collaborative project involving multiple space agencies including NASA, ESA, Roscosmos, JAXA, and CSA, has been vital for international cooperation in space. Since its launch in 1998, the ISS has utilized advanced communication systems to ensure continuous contact with Earth. This includes both traditional radio communication and satellite-based systems that support video data and voice transmissions. The technologies developed for the ISS have informed subsequent missions to Mars and other celestial bodies, emphasizing the significance of reliable communication in maintaining operations and ensuring crew safety in extreme environments. The establishment of a Mars communication network by 2025 is poised to revolutionize our capability for seamless connectivity between Earth and Mars, especially as human endeavors in space exploration accelerate. This initiative is driven by the need for reliable communication to support numerous missions, including crewed expeditions to Mars and robotic explorations. Future outlook and predictions. 1. Enhanced communication capabilities. By 2025, we can expect the implementation of advanced laser communication systems that will significantly increase data transfer rates between Mars and Earth. Traditional radio communication methods typically face challenges such as lower bandwidth and higher latency. The integration of laser communication can potentially reduce latency to mere minutes, facilitating near real-time interactions that were previously unattainable. This will enable critical data exchange during missions, including real-time telemetry for astronaut health and environment monitoring. 2. Advanced satellite network deployment. The deployment of a robust constellation of satellites orbiting Mars will create a comprehensive communication network. By leveraging a mix of low Earth orbit and geostationary satellites, we will achieve continuous coverage across the Martian surface. This satellite network will be crucial in ensuring that all missions, both crewed and uncrewed, can maintain constant contact with mission control on Earth, thereby enhancing mission safety and operational efficiency. By 2025, it's anticipated that multiple satellites will be operational, setting the foundation for ongoing expansion and upgrades as technology advances. 3. Autonomous routing systems. The development of autonomous routing systems will play a pivotal role in managing data traffic efficiently. These systems will utilize artificial intelligence to determine the most effective pathways for data transmission in real time, adapting to the dynamic conditions of space. By 2025, we predict that these systems will be fully operational, minimizing data loss and maximizing communication reliability. Furthermore, their adaptability will allow for quick responses to unforeseen challenges, such as satellite malfunctions or changes in mission parameters. 4. International collaboration. A successful Mars communication network will not only depend on technological advancements but also on international collaboration among various space agencies, private sector partners, and academic institutions. By 2025, we can foresee the establishment of a collaborative framework that will pool resources and expertise. This coalition will be essential for the timely development and deployment of the necessary infrastructure, ensuring that all stakeholders are aligned on mission objectives and technological standards. 5. Increased investment in space exploration. The proposed $500 million investment is just the beginning. As the benefits of reliable communication systems become evident, we can expect increased investment from both public and private sectors. This financial influx will accelerate research and development, leading to innovations that extend beyond Mars missions and into broader space exploration initiatives. The investment will also stimulate the growth of the space technology industry, creating jobs and fostering new technologies that can be applied in other sectors. 6. Expansion of commercial applications. The advancements in Mars communication technology will likely spur a wave of commercial applications. Companies specializing in satellite communications, data analytics, and space technology will emerge, leading to new business models and revenue streams. By 2025, we might see startups focusing on providing communication solutions not only for Mars but also for lunar missions and other planetary explorations, enhancing our overall capabilities in space. 7. Interplanetary communication standards. With the establishment of a communication network for Mars, the groundwork will be laid for creating interplanetary communication standards. By 2025, we should expect discussions and agreements among international space agencies regarding best practices and protocols for interplanetary communication. This will ensure interoperability between various missions and facilitate future endeavors beyond Mars. Conclusion. The establishment of a Mars communication network by 2025 represents a significant leap forward in our ability to explore and understand our neighboring planet. Through the integration of advanced laser communications satellite networks and autonomous routing systems combined with international collaboration and increased investment, we are not only preparing for Mars missions but also paving the way for a future of deeper space exploration. The implications of this initiative will resonate not just in the realm of space exploration but also across various sectors on Earth, heralding a new era of technological advancement and commercial opportunity.